Today we'll be working on finding the derivative of an ln function and the derivative of an exponential or e function. Let's start with our exponential function, which in our case is equal to e to the power of cos x. This is a good example of an exponential function, as it would also help us to understand how deriving trigonometric functions work, because it contains this cos right here. To make the rule for deriving e functions easier to understand, I'm going to replace our cos with a u, so that we will be left with y is equal to e to the power of u of x. You can see why I've done this now, as the rule for deriving exponential functions states that when deriving the function, we simply rewrite our e to the power of u of x, our original function, and we then multiply it by u dash of x, so the derivative of our u of x part. In our case, this is the derivative of cos x. Now that we know the rule for deriving an exponential function, we can answer our question. First thing we do is rewrite our e to the power of u of x. I've rewritten our e to the power of cos x, the original function. Next, we have to multiply this by the derivative of our u of x, which means the derivative of cos x. Now the derivative of cos x is minus sin x. Therefore, our answer is e cos x multiplied by minus sin x. And that's how we derive an exponential function. This is our answer right here. So let's try and differentiate the ln function now. When deriving an ln function, we follow this simple and easy to follow rule. dy dx is equal to 1 over fx by f dash of x. What this rule means is that to find the derivative of an ln function, we must put 1 over whatever value comes after the ln. In our case, this is equal to x to the power of minus 3 by e to the power of x squared. This value will take the place of the fx in the rule on screen. The next part is the tricky bit. We must take our value for fx and find its derivative. Once we've done that, we can then multiply it by our 1 over fx. That is to say that the derivative of fx is filling the place of the f dash of x in the rule on screen. Okay, so now that we know how the rule for deriving ln functions work, we can start answering our question. First things first, we've got to find out what our value for fx is. Well, that's easy. All you have to do there is look at the value after the ln, which in our case is equal to x to the power of minus 3 by e to the power of x squared. Now that we have our fx value, our next step is to find its derivative, so as to find a value for f dash of x. We notice that our fx value has two parts, e to the power of x squared and x to the power of minus 3. We also notice that they are multiplied by each other. To get the derivative of a function where two values are multiplied by each other, we use the product rule. To make this rule easier to explain, I'm going to put our x to the power of minus 3 equal to u and our e to the power of x squared equal to v, so that in the end I'm left with fx or y is equal to u by v. Now we can find the derivative of fx by using the product rule. To follow this rule, we must take the derivative of our u value, so du dx, and we multiply that by our v value. We then add this to the derivative of our v value, dv dx, multiplied by our u value. When all of this has been done, we will be left with our derivative of fx, or our f dash of x as it's called. So let's give this a shot. Our fx value is x to the power of minus 3 by e to the power of x squared, and we have broken it into two parts so that u is equal to x to the power of minus 3 and v is equal to e to the power of x squared. We will now follow the product rule to get our answer. Let's complete the left hand side of this rule first. Our du dx value is simply the derivative of our u value, x to the power of minus 3. To derive this, all we have to do is take the to the power of minus 3 down and multiply it by x, and then drop our power value by 1, so that in the end we are left with minus 3x to the power of minus 4, as you can see here. We then multiply this by our value for v, which is e to the power of x squared, and then we are then left with minus 3x to the power of minus 4 by e to the power of x squared. Now let's move on to the right hand side. We follow the same process here, but this time we get the derivative of our v value and multiply it by our u value. This means that we have to derive e to the power of x squared. As we learned earlier in this video, to derive an e to the power of ux function, we simply multiply the function by the derivative of our value for u of x. In this case, it means that we are going to multiply the derivative of x squared by e to the power of x squared. The derivative of x squared is 2x, as we multiply our x by our power value, which is 2, and we then drop our power value by 1, which leaves us with 2 by x to the power of 2 minus 1, which is the same as 2x to the power of 1, which we can write as 2x. So we then multiply this 2x by e to the power of x squared, so that we are left with 2x by e to the power of x squared. So that's our dv dx calculated. So all we need to do now is multiply it by our u value. When we have done this, we are left with x to the power of minus 3 by 2x by e to the power of x squared. However, we can simplify this value. We can multiply x to the power of minus 3 by 2x simply by adding their powers together. 2x can be written as 2 by x to the power of 1, as x to the power of 1 is equal to x. We can multiply x to the power of 1 by x to the power of minus 3 by adding their powers together, so that we are left with x to the power of minus 3 plus 1, or x to the power of minus 2. We then multiply this by our 2, and then again by our e to the power of x squared, so that we are left with 2x to the power of minus 2 by e to the power of x squared. And that's our right hand side of the product rule finished now as well. All we need to do now is add our left hand side and our right hand side together to get our value for f dash of x. We can see that e to the power of x squared is a common factor in both sides. So we can take this out and be left with e to the power of x squared brackets 2x to the power of minus 2 minus 3x to the power of minus 4 bracket. Again, using the rules of indices, we can rewrite or simplify this as e to the power of x squared by 2x squared minus 3 all over x to the power of 4, as 2x to the power of minus 2 is equal to 2x squared over x to the power of 4, and minus 3x to the power of minus 4 is equal to minus 3 over x to the power of 4. So now we have our value for fx and our value for f dash of x. To complete the function, all we have to do is add them into our rule for ln function dy dx equals 1 over fx by f dash of x. When we do this, we are left with 1 over x to the power of minus 3 by e to the power of x squared multiplied by e to the power of x squared times 2x squared minus 3 all over x to the power of 4. Technically speaking, this is our answer. This is a valid answer. But we're going to try and simplify this. To do this, we multiply both our fractions by each other so that we are left with only one fraction, which is much easier to work with. We can see that e to the power of x squared is on top and on the bottom of our fraction. So we can cancel that out, those both out. Also, at the bottom of our fraction, we notice that we have two x values multiplied by each other. We learned earlier that we can multiply these values together simply by adding their powers together through the rules of indices, so that we have x to the power of 4 plus minus 3, which is the same as x to the power of 4 minus 3, which is equal to x to the power of 1, or x. So after all of that, we are left with dy dx is equal to 2x squared minus 3 over x. Now isn't that a lot neater and easier to read than this big thing up here? We can in fact break this down a little bit further by breaking our fraction into 2, leaving us with 2x squared over x minus 3 over x. But 2x squared divided by x is equal to 2x. So in the end, we will be left with dy dx is equal to 2x minus 3 over x. And that's it. We've finished deriving our ln function.